Poisson Compositing. Let us look at the problem we address. As we all know, real-world scenes can take enormous range of brightness levels. That is, they have high dynamic range. However, common cameras, printers, displays can represent only limited dynamic range. Then, how shall we visualize real-world scenes using common devices which are compatible only with low dynamic range or LDR images? Here is an illustration of a scene which has a very high dynamic range. We usually capture multiple differently exposed images to span the entire dynamic range of the scene and composite them. This process, traditionally called high dynamic range imaging, requires the knowledge of camera response function. We estimate camera response function called CRF first from multiple differently exposed images. We then compute certainty function, which is the derivative of camera response function. We linearize the intensities using camera response function and weigh them in the irradiance domain using certainty function. The generated HDR image needs to be tone mapped for making it compatible with common displays and printers. Here are the related references for high dynamic range imaging. Alternately, one can composite the images in the image domain itself. Here is the method. We do not require the knowledge of either the camera response function or the exposure settings. The generated image is low dynamic range compatible with the common displays and printers. These are the related works which solve the high dynamic range imaging problem in the image domain itself. Here are the problems with these methods. Exposure fusion requires compositing at multiple scales and tends to reduce the overall contrast of the generated LDR image. Variational compositing does not provide explicit weighting function, and being iterative, it is slow compared to the other existing methods. Bilateral compositing depends only on the texture information in the images and tends to reduce the brightness of the generated LDR image. We propose a novel method to solve this problem. We shall get some background behind gradient domain processing. We consider image as a scalar field and use gradient operator to get the gradient vector field, which is conservative. Once we do some manipulations on the gradient field, it becomes non-conservative. We must use Poisson solver to reconstruct the scalar field from the modified gradient field. Advantages of this approach include seamless image editing and compositing, easy implementation, and fast computation when direct Poisson solver is used. Here are some of the relevant applications solved in the gradient domain. We shall now look at the methodology behind compositing performed on the gradient fields. We compute the weighting function or MAD from the input images and their gradient fields and use it to weigh the gradient fields. The resultant non-conservative gradient field is processed using a Poisson solver to get the desired composite image. We shall now apply the gradient domain processing to solve the HDR problem. The highlighted blocks show our contribution in this work. Apart from designing the weighting function to weigh the gradient fields, we also pre-process the gradient fields. Pre-processing of the gradient fields is done to brighten the underexposed and darken the overexposed images. We employ the function used by Perez et al. In Poisson image editing to vary the local illumination as shown here. Alpha is the average gradient field magnitude. We do this operation for each of the gradient fields corresponding to the multiple differently exposed images. This operation can be better explained using this diagram. Value of beta less than 0 darkens the image and the value of beta greater than 0 brightens the image. We use negative beta values for the overexposed images and positive values for the underexposed images as shown in this figure. Now we shall see the design of weighting function to composite the modified gradient fields. We have two components in the weighting function, the brightness term and the contrast term. The brightness term is a Gaussian function of the intensity values as shown here. This function gives more weight to the well-exposed regions while penalizing the overexposed and underexposed regions. The contrast term is the local mean of the gradient magnitudes, which provides more weight to the gradient fields of those images with more local contrast. We design the weighting function as the convex combination of the sum and product of the brightness and the contrast terms. Let us now see how we reconstruct the final image, which is a scalar field, from the resultant non-conservative gradient field. We use the direct Poisson solver with Neumann boundary conditions to achieve this task. The direct Poisson solver is used as it is the fastest. We shall now look at some of the results. This is the computational overhead shown with other methods. We can see that our approach is comparable in speed with the existing fastest method. Here we show the 9 multi-exposure images and the composite result using the proposed approach. We can visualize that the brightness, contrast, and color are well preserved. Here is the comparison with other methods. We can observe that the proposed approach generates high quality LDR image better than the existing methods. Here is another set of multi-exposure images corresponding to a HDR scene. Here are the LDR images generated using various methods. We can observe that the proposed approach produces superior results. Here is another set of multi-exposure images corresponding to a HDR scene. Again, from results it is evident that the proposed approach performs very well compared to the other methods. Here are the conclusions. Our approach is very fast and accurate and provides seamless reconstruction of the LDR image. We do not require the knowledge of camera response function. As seen in the results, the quality of generated LDR images is much better than that of the existing methods. Thank you.